All right, so our question now is if I do know that a vector field is conservative, how can we find the potential function? Well, if we think about what it means, right, being conservative means that you are a gradient of some function, which means that your components are partial derivatives. So if we're going to try and go backwards and find that potential function, we're going to need to do some integration. So let's look at an example. Show that the vector valued function f of xy equals 3x squared y squared I plus 2x cubed yj is conservative, and then find its potential function. So we're just going to kind of learn through an example. So first off, to show that it's conservative, this is what we learned last time. So we need to do the partial of m. M is the x component, so we're going to do that with respect to y. So this is the partial with respect to y of the x component is 3x squared y squared. So that partial with respect to y, we're going to bring the 2 down from y, making it 6x squared, drop the power to a y. And then we take the partial of n, which is the y component, so we do it with respect to x. Because keep in mind, you're trying to essentially see, are they mixed partials? So the partial with respect to x of 2x cubed y. So now we're doing it with respect to x, so the power 3 comes down to make 6x squared, and then we keep the y. So notice they are both equal to 6x squared. So since those partials of m with respect to y equals the partial of n with respect to x, capital F is conservative. So now to find the potential function, let's call it little f. Well, think about the fact that we need little f. If we took its partial with respect to x, we should get the first component of f, which is that m component. So that would mean that the partial of little f with respect to x should be 3x squared y squared, and the partial of f with respect to y should be n. It should be the second component, which in this example is 2x cubed y. So let's start with the first one, and let's try and go backwards. So when we took the derivative, the partial derivative with respect to x, well, we got that expression. So let's do an integral with respect to x. So let's first do the integral of m, which is that really the partial with respect to x, dx. So we're taking that first component and taking the integral with respect to x. Since really, another way to write this, right, this should be f sub x, and this one should be f sub y. So another way to write this is we're taking that integral of f sub x with respect to x. So that's the integral of 3x squared y squared dx. So remember, y's we just treat as constants. So then we'll keep the 3y squared. The power on x is going to increase to a 3, and we divide by that new power. So we really have x cubed y squared. And then remember, we need plus a constant, but really in this case, a constant is anything that's truly scalar, so truly a constant in the sense that we're used to, or strictly in terms of y. So remember, what you get is you get a plus some function, say c of y, plus some function of y. Okay, so what we get then at this point is this should be our expression of the little f function, but yet we don't know the rest of it, right? There's a lot of things that could be in here that technically would all still make this partial derivative with respect to x work, but we also need the other one to work. We need the partial with respect to y to work. So let's say that this is f. Now what I want to look at is now find the derivative of that f that we just found. So let's maybe call it f1. It was our little first step. Well, that's going to be the partial derivative with respect to y of x cubed y squared plus some c of y function. Which the first part of that will bring the 2 down, so we're going to get 2x cubed y. And then we're just going to have a derivative. We don't know what the second piece is. We don't know what expression it is, but it's some expression of y. So it's just going to be some c prime of y. Now, if we think about what we need, is we need this to be n. We need that to be that little f sub y. It should be the same. So let's set them equal. So n up top, f sub y, was 2x cubed y. And then this new expression we just got is 2x cubed y, but plus c prime of y. So now we're thinking about that equation, and thinking about how to make that equation true. We'll notice that some of the parts are corresponding, right? Both of them have a 2x cubed y. So we can cancel that on both sides. So then what we're left with is that we would need c prime of y to be 0. We need that piece to go away. The goal of all of this is we need to find this c of y. So we need to find this. Well, I know its derivative is 0, so if I need to find c, we need to integrate again. But this time, the way that we got that c prime was we did it by taking a derivative with respect to y. So we need to integrate with respect to y. So the integral of c prime of y dy is the integral of 0 dy. And when I integrate 0, well, we get 0, but we also get plus a constant. We always get that plus a constant when we do a single integral. Now, in this case, we weren't integrating a multivariable function. Notice it was just a function of y. So there's no x's in this one. It's just functions of y. So this c is truly a scalar. So this is a scalar c. So then what we have is that f of xy is going to be, we've had that 2x cubed, that was the derivative. We had f from over here, so this is this guy. We had x cubed y squared plus c, which is what this guy would be. This would be c of y. And it turns out that c of y is just a constant, so plus a constant c. It kind of makes sense that in the end, we don't get a unique function, because really we're still doing antiderivatives, right? And antiderivatives give families of functions that all just differ by a constant. Since we're doing derivatives, any plus a constant, a plus a scalar at the end of the function in both derivatives is just going to go away. So we could pick any specific constant there, and this will still work as a potential function. So we essentially get a family of potential functions. What we could do if we knew more information, if we knew some like initial conditions, we could try and solve for that constant c in particular scenarios. But in a generic scenario, there is no particular c. It is just the family of all scalars added are possible. So we're going to try one more example of this to kind of get a feel for it. But essentially, it's sort of like we're working one way, right? We do one of the antiderivatives to sort of look for, well, what does the function look like? But then we're left with this extra piece of it that we need to solve for. So then we need to take the derivative of that guy and match it up with the other derivative to make it work with the second partial derivative that we're looking at. So we'll try one more example to kind of get a little more of a feel for this.